Hello and very welcome. Today we will be looking at what I call the driven pendulum rod. We are busy with the postgraduate module Dynamics with the acronym msd780, and this is the third lecture in the module. My name is Dr. Lucas du Plessis and I'm a senior lecturer in the Department of Mechanical and Aeronautical Engineering at the University of Pretoria. So what you see on the screen now is on the left hand side a schematic of the driven pendulum rod. It pivots here at point A, and there is a counterclockwise moment acting on the pendulum rod, which will cause the pendulum rod to then also start from rest and rotate counterclockwise about point A. Right. The rest or the mass properties of the pendulum rod is the same as what we've discussed and what we considered in the previous lecture. So the mass is 2 kilograms. The moment of inertia about the center of gravity is given by this formula, 1/12 times the mass times the length squared, which equates to 0.06 kilogram meters squared. The angular acceleration that we want to achieve is 2 pi over 60 radians per second squared, and we find the angular velocity by integrating this expression or this constant angular acceleration, and that yields this equation or this expression given over here. So the angular velocity phi1 dot as a function of time equals 0 plus 2 pi over 60 times t radians per second, and that simplifies to 2 pi over 60 times t radians per second, and you can obviously eliminate the 2 above the line, so it will be pi over 30 times t radians per second. And if we integrate this expression once more, we get an expression for the angle or the orientation of body 1 as a function of t, and that's given over here. So it will be our initial orientation, which is shown here in the schematic on the left hand side. Phi 1 initially is minus 30 degrees, and that is minus pi over 6 radians, plus then it's the integral or this expression that has been integrated, so it will be 1/2 times 2 pi over 60 times t squared radians, and that can simplify to what you see on the right hand side of the equation here. So the orientation of body 1 as a function of time is minus pi over 6 plus pi over 60 times t squared radians. All right. We can also calculate the initial coordinates of body 1, the x and y coordinates at time t0. That is simply given by we take this length, which is 0.3, because the total length of the pendulum, the driven pendulum rod, is 0.6 meters. So half of that is 0.3 times cosine of minus pi over 6. Okay, and that will give you the coordinate 0.25981. And if we look at it geometrically, the origin of the xy coordinate system is here at point A, and the x coordinate of body 1 at time t0 is obviously a positive value. So this, if we do a sanity check on this value that we obtained, it does indeed make sense. Now similarly, the y coordinate, we can take 0.3 times sine of minus pi over 6, and now we end up with a calculated value of minus 0.15 meters. So if we once again do a sanity check, the y coordinate of body 1 must indeed be less than 0, and so this value makes sense. Now we want to know at time t0 what is the torque that we need to apply in order to achieve an angular acceleration of 2 pi over 60 radians per second squared. Okay, so in order to do that, we take sum of the moments about point A, and that is simply equal to the moment of inertia of the pendulum rod about point A multiplied by the angular acceleration of body 1. So IA, and we distinguish here between IA, the moment of inertia of the pendulum rod about point A. We distinguish that from the moment of inertia of the pendulum rod about the center of gravity, which is what we have here initially. We looked at the moment of inertia of the pendulum rod about the center of gravity. Right, so this is different. The equation for that moment of inertia is 1 over 3 times the mass times the length squared. And if we substitute the values, we get 0.24 multiplied by the angular acceleration, and we get a value of 0.02513. Okay, so if we now look at the moments, or the moments as a result of the forces that act on the body, then it's easy to see that sum of the moments about point A equals this moment n, written down over here, and then there's the moment caused by the weight of the pendulum rod. The moment arm of this component is L over 2, so it's easy to see positive is counterclockwise, so plus n minus mg cosine 30, which is this component over here, multiplied by the moment arm, L over 2, which is shown here. We can substitute the values, and we get then the value for the moment that is required to cause an angular acceleration of the driven pendulum rod of 2 pi over 60 radians per second squared is 5,1226 Newton meter, and that's in a counterclockwise direction as indicated here in the figure. So if we look at the reaction forces, to calculate the reaction forces here at revolute joint or pin joint A, we can take the sum of moments in the Kc direction, Kc being perpendicular to the orientation of the driven pendulum rod, and that will be the mass of the pendulum rod multiplied by the acceleration in the Kc direction. Okay, so the forces acting on the driven pendulum rod are obviously this force here indicated here, F Kc, and then in the negative Kc direction it is mass times gravitational acceleration times cosine 30. Okay, and then those are the only forces acting in the Kc direction, and that will be equal to the mass of the pendulum rod multiplied by the acceleration in the Kc direction. Now, seeing that this pendulum rod is driven to accelerate at an angular acceleration of 2 pi over 60 radians per second squared, we can say that the acceleration in that positive Kc direction at time t0 is equal to this length over here, which is L over 2 multiplied, it's this one over here, multiplied by the angular acceleration phi 1 double dot. That's the component of the acceleration in the positive Kc direction at time t0. So we can substitute the values as you can see here in this expression over here, and we end up with a final value of 17,054 Newton in the direction indicated on the diagram. Okay, similarly, we can take sum of the forces in the eta direction. That equals mass times the acceleration in the eta direction. So the forces acting in the eta direction is this force indicated here in green on the diagram. That's positive eta, F eta in the positive eta direction, and then in the this component of the weight, mass times gravitational acceleration times sine of 30 degrees, that's acting in the negative eta direction, and that's why we have minus mass times gravitational acceleration times sine 30 degrees. That equals the mass of the pendulum rod multiplied by the acceleration in the eta direction. So in the eta direction, with the pendulum rod being driven in the counterclockwise direction, causing an angular acceleration of 2 pi over 60 radians per second squared, there's also a component of acceleration in the positive eta direction, which equals this distance over here, L over 2, multiplied by the angular velocity squared. Okay, and that's what you see over here. So we know the pendulum rod starts from rest, so even though it has an angular acceleration, the angular velocity will be 0, so we can eliminate this term over here. But if we substitute the other values, the mass 2 kilograms, gravitational acceleration sine theta or sine 30 degrees, we get the reaction force in the eta direction as indicated here in the positive eta direction is 9,81 newtons. Okay, and then using trigonometry we can find the reaction forces in the x and y directions. As you can see over here, we simply take the c component multiplied by sine 30 minus the eta component of the reaction force times cosine of 30 degrees. We end up with F in the x direction, the reaction force in the x direction 0,0314 Newton. And similarly in the y direction it's 19,674 newtons. Okay, so if we consider the driver function, that will result in a constant angular acceleration of 2 pi over 60 radians per second squared, then we will end up with the situation as depicted on the right hand side of what you see on the screen. So firstly, the angular acceleration, as we know, is a constant 2 pi over 60 radians per second squared. That is approximately equal to 0,105 radians per second squared. So by integrating this expression, we get the expression for the angular velocity, and it's either the accurate expression is 2 pi over 60 times t radians per second, which is approximately equal to 0,105 times t radians per second. Now, integrating this once more, we get the accurate expression is the initial value minus pi over 6, which is minus 30 degrees, plus pi over 60 t times t squared radians. Okay, and that's approximately equal to minus 0,524 plus 0,105 divided by 2 times t squared radians. So another way of, and you will see in a minute why I'm including this portion over here, we can say phi 1 as a function of time equals c1 plus c2t plus c3t squared. And it's very easy to then derive to the equations given here at the bottom, or the expressions. C1 is minus pi over 6, or approximately minus 0.524. C2 is 0, and C3 is pi over 60, or approximately 0.105 divided by 2. Okay, so let's now simulate, or simulate is the right word. Let's simulate the driven pendulum rod using Prof. Newton-Raphson's Matlab code. And as I've explained in lecture 2, what you need to do is copy and paste one of the existing model subfolders and then edit these input files. Okay, so I've already opened the input files on the right hand side of my screen. So, and they are now listed here in alphabetic order as they are listed in the model subfolder. Okay, so the first function is inanimate. This file contains the variables defining the 3D animation axis. Okay, and for our driven pendulum, what I suggest we do is we specify x min and y min as minus 0.75 meters, and x max and y max as 0.75 positive 0.75 meters. The reason for that is, if I can show you this PDF, we are expecting this driven pendulum rod to rotate in a counterclockwise direction. So the length of the pendulum rod is 0.6 meters, as shown here in this hand-drawn schematic. So if we animate in Matlab, if we have an animation window with extremities of plus 0.75, minus 0.75, plus 0.75 and minus 0.5, that should work very well. Okay, so that explains our first input file. Then in bodies, and this is exactly the same as before, so or what I've explained in lecture 2. Let me just run through it quickly. So the mass is 2 kilograms. The moment of inertia about the center of gravity is 0.06 kilogram meter square. If I can quickly show you, mass 2 kilograms, moment of inertia about the center of gravity 0.6 kilogram meter square, and it was calculated as I was explained earlier in this lecture as well. Right, so initial position for body 1, that's in meters, 0.2598 in the x direction, minus 0.15, and the initial orientation minus pi over 6, or minus 30 degrees. Okay, and this is I showed in lecture 2 using CAD how we could find those coordinates. In this lecture we already showed how we can actually calculate those values. x1 at time t0 is 0.25981, and the y coordinate at time t0 is minus 0.15. And as we've already mentioned a number of times, the initial orientation is minus 30 degrees, or minus pi over 6 radians. The way that Newton-Raphson's algorithm works is we start with the positive x direction and we measure any orientation angle in a positive direction counterclockwise. So in this case the orientation is measured in a clockwise orientation, so that's why it's minus 30 degrees, or minus pi over 6 radians. Minus pi over 6 radians. Right, so yes, that's the body input file. Now I've commented out the initial velocity of body 1 because 0, 0 here in the body input file or in bodies is in any case the default. If you don't specify anything for the initial velocities, this is the default, okay, which is in our case, our pendulum rod starts from rest, so we can either specify the initial velocities as 0, 0, the x and y components, or we can simply leave it out. The default value for the initial velocities is 0. If you don't specify anything, it's 0. Alright, so we only have one body, and that's why our list contains only a single entry, B1. Okay, so now in forces, this is the Matlab input file in forces. This looks exactly the same as we had previously with lecture 2. So it's only weight that's being applied. That's the only force acting on the system. Okay, now I will talk about the input file in funcs a little bit later. Let's jump to in joints. You will recognize the first part of this input file is exactly the same as what we had before. We have indeed still a revolute joint, that's the type. Then this is joint 1, the type of joint 1 is revolute. Joint 1 IP index or I point index is point number 1, and joint 1 JP index or J point index is 2. Just to recap quickly where points 1 and 2 lie, let's quickly have a look at hand-drawn schematics. So points 1 and 2 coincide at the location of the pin or revolute joint. The difference is point 1 is on ground, which is body 0, and point 2 is on the pendulum rod, which is body 1. Okay, point 3 is also on the pendulum rod or body 1, and this is the location of point 3. Okay, so P1 is on body 0 or ground. It's at local coordinates 0, 0. I explained this in a lot of detail in lecture 2. So point P2 is on body 1, and it is at local coordinates minus 0,30. Okay, and similarly point P3 is also on body 1. It's at local coordinates plus 0,30. Okay, and let me just quickly show that again. So for body 0, the global coordinate system coincides also with the position of, with the location of the pin joint. And as I said before, point 1, which is on ground, also coincides with that point. So it makes sense that the local coordinates in ground of point 1 is at coordinates 0, 0. But point 2 is on the pendulum rod, and it is at location minus 0,3 in the KC direction and 0 in the eta direction. And point 3 is at plus 0,3 in the KC direction and 0 in the eta direction. Joint 2 is new. This is specified specifically so that we can prescribe the angular rotation that you see on the screen. How this was specified, we started with a constant angular acceleration. That is what we want. We want a constant angular acceleration of the pendulum rod at 2 pi over 60 radians per second squared. Okay, that will, if you integrate that, you get a linear angular velocity of 2 pi over 60 multiplied by t radians per second, and if you integrate that, you get a quadratic function of the rotational angle of body 1 starting at minus 0,524 or minus pi over 60 radians plus pi over 60 t squared radians. That's the rotational angle of the pendulum rod. Okay, so this is the behavior that we want to specify, and what we are busy with, we want to calculate what is the required moment that will result in this angular response. So the way we do that in Newton-Raphson's algorithm is we specify a specific joint type, which is referred to as a relative rotation joint. Okay, and it's between IB index or I body index 1. Okay, if you remember, the pendulum rod is body 1 and J body index is 0. That's ground. So the relative rotation is between the pendulum rod and ground, and we specify it as shown over here. Okay, and then we need to specify a function for this joint. Okay, and we refer to it, or we number it as function 1, and we'll get to the function in a minute. Okay, lastly, it's important to then list both joints that we've specified as done here on the screen. Let's now have a look at the input file in func. Okay, so the function type is what Newton-Raphson refers to as type A. Newton-Raphson also or formulated what he refers to as a type B and a type C function, but we'll get to that in a later lecture. For function type A, the only thing we need to specify, apart from the fact that it is function type A, are the 3 coefficients. Okay, this is the first coefficient, minus 0,5236. The second coefficient is 0,0 or 0, and the last coefficient is 0,05236. Right, so let's just confirm how we got to that. Right, so this coefficient C1 is minus pi over 6 minus, or approximately minus 0,524. Okay, and that's what you see on the screen here, minus approximately 0,524. Okay, our C2 is 0,0, which is exactly what we determined previously, and our C3 coefficient is 0,05234, okay, which is 0,105 divided by 2. Okay, the last Matlab input file that we have to consider is the function in U vectors, and that's as before with lecture 2, it's an empty list. Okay, so we are now ready to run the simulation. So in order to do that, we go to command window and we enter DAP. Let me just move this a little bit. It then asks which folder contains the model, and for our case it is pendulum rod subscript D. it asks if we want to correct the initial conditions, and yes, we do want to do that. So here you can see the corrected x and y coordinates are as expected, or plus 0,259808 in the x direction, minus 0,15, and the initial orientation is minus 30 degrees. The corrected velocities are 0, 0, 0 for the x dot, y dot, and phi dot. Right, then it asks for the final time, and we can use 30 seconds. The reporting time step, we will use 0,06 so that we have 500 time steps for the duration of the simulation. Okay, we press enter, and there the simulation ran. So in order to look at an animation of the simulated results, we type in the word anim, or the letters A-N-I-M. Okay, then you have to click in the command window and press enter, and there you can now see the animation. Alright, and as expected, the pendulum rod starts slowly and accelerates angularly at a rate of 2 pi over 60 radians per second squared. That's what's specified. Obviously, that is not something we can detect in the animation. All we can see is that it is accelerating angularly. Okay, and once again, what you can also see here is the fact that our plot window is correctly chosen. Plus 0.75 in the x, minus 0.75 in the y. X is plus 0.75 minus 0.75, and y also plus 0.75 minus 0.75. Right, so let's just give it a few seconds more to finish. There we go. Alright, so now we want to look at our results. So in order to do that, we type in the word post. Okay, so we are obviously very interested in the reaction forces and the torque that is required in order to yield the specified angular acceleration. So in order to do that, we click on the variable lamb. This variable shows the Lagrange multipliers at each time instant from time t0 to time 30 seconds in increments of 0,06 or 60 milliseconds. Right, so what I did then offline is I copied and pasted these Lagrange multipliers into the Excel spreadsheet. You can of course also plot the Lagrange multipliers or any of the other variables inside Matlab, but I prefer to do it in an Excel or in a spreadsheet rather. I use LibreOffice Calc. So that's what you see on the screen here, the Lagrange multipliers, the plot of them. So let's just talk about the trends that we can identify. You can see Lagrange multiplier 1, 2, and 3. 1 is in blue, and 2 is in red, and 3 is in green. Okay, and 3 is also indicated on the secondary y-axis. Lagrange multipliers 1 and 2 are indicated, or yes, are labeled on the primary y-axis. Right. So what we see is we start with an initial initial values for Lagrange multipliers 1 and 2. It then starts oscillating. The amplitude of oscillation increases and the period of oscillation decreases as we progress from 0 to 30 seconds. Okay. Now, Lagrange multipliers 1 and 2, as you'll see later on in this lecture, are used to calculate the reaction forces. Okay. Okay, let's quickly have a look at the magnitudes of the Lagrange multipliers at time t0. So if I zoom in a little bit, that's what you see over here. And let's focus for now on Lagrange multipliers 1 and 2. So okay, analytically we've calculated that the reaction forces in the x and y directions are given by 0 in the x direction 0,0314 and in the y direction 19,674, and both of them are in the positive directions as indicated in the schematic on the left hand side. Okay, so now the Lagrange multipliers, just as in lecture 2, exactly the same as in lecture 2, these Lagrange multipliers have the same magnitude as the reaction forces or calculated reaction forces, but the signs are negative. Okay, and at the end of the lecture you will see why this is the case. Okay, but again, if I can just put both of them on the same screen. As you can see, lambda 1 corresponds magnitude-wise with fx 0,314, and lambda 2 corresponds to fy in magnitude, again 19,674. Right. So that is Lagrange multipliers 1 and 2. Let's quickly have a look at Lagrange multiplier number 3 at time t0, and we see a magnitude of 5,1226. Right, so if we look at our analytical calculation for the moment that we need in order to generate the specified rotational behavior is 5,1226. So Lagrange multiplier 3 corresponds also magnitude-wise with the calculated moment as well as the sign. The sign is the same. And if you bear with me just for a little bit, at the end of this lecture, I'll explain why this is the case. So to wrap up this portion of the lecture, let's quickly look at the other results. What you see on the screen is a plot of the x-y coordinates of the C of G of body 1, or the center of gravity of body 1. The aspect ratio is wrong, but you can clearly see that the center of gravity intersects the positive y-axis at 0,3, negative x at minus 0,3, negative y at minus 0,3, and positive x at plus 0,3. So this is exactly what we expect for our pendulum rod, rotating counterclockwise. If you remember, the total length is 600 millimeters or 0,6 meter. So the radial distance from point A to the C of G is 0,3 meters or 300 millimeters. So that's why the trace of the C of G is exactly as expected. Okay, so the coordinates, x and y coordinates, are plotted against the primary y-axis, and the orientation angle phi is plotted on the secondary y-axis on the right hand side. So let's quickly look at the x and y coordinates. So as expected, an oscillating behavior is what we can see, and it varies between plus 0,3 and minus 0,3, and the periods of these oscillations get shorter and shorter as time goes by, and that's because of the constant angular acceleration. So this corresponds to what we expect. In terms of the orientation angle, it's not clearly visible, but we start at minus 30 degrees, and then it increases at an quadratic rate over time all the way to more than 2,500 degrees. So this corresponds exactly to our behavior over here. This is now in radians. It starts at minus 0,524 and it increases quadratically as time goes by. Right, so let's quickly look at the velocities. Both x and y components of the velocity start at 0, oscillating behavior, but over here with the velocities, the amplitude of the oscillations increase as time goes by, and once again the period of the oscillations decrease. The angular, and this is what we expect really in terms of the angular velocity of the pendulum rod. We start at 0. This is again plotted on the secondary y-axis. So we start at 0 and we increase linearly as time goes by. So accelerations, let me just quickly show you that. Accelerations, same or similar behavior as velocities, start at a certain magnitude at time t0. So they start at a specific magnitude. They then oscillate with an increasing amplitude and a decreasing period. Okay, and the angular acceleration on the secondary y-axis is constant and it's just over 0,1. If I can just go back to what we said here, as expected, it is 2 pi over 60 radians per second square, constant. 2 pi over 60 equals 0,105 rounded to 3 decimals. Alright, so that's exactly what we see on our graph over here. Okay, so let's now look at the mathematics behind the analysis of the driven pendulum rod. I'm using the same mind map as before. I've added some details in the sections 3 and 4, but I'll refer to those details as we go along. For now, we're going to look at section 5, the kinematic and inverse dynamic analyses of the driven pendulum rod using Newton-Raphson's body coordinate formulation. And the details are also explained in Newton-Raphson's textbook, Planar Multibody Dynamics, Revision 2, in chapter 12. Alright, so let's jump right in. First of all, we'll look at what is called, or what Prof. Newton-Raphson refers to as the kinematic analysis. So, kinematic analysis by definition is the solution of coordinates, velocities and accelerations of closed chain systems by solving the constraint equations. When kinematic analysis is considered for a mechanism that has 1 degree of freedom, then one driver constraint is included in the formulation. Now, based on the motion described by the driver, the kinematics of the entire system can be solved for. Okay, and that's exactly also what we have with the driven pendulum. Okay, so the second line of thought is, regardless of the choice of coordinates for a multi-body system with n degrees of freedom and nv defined coordinates, if the number of defined coordinates nv is greater than the degrees of freedom, then there must be n subscript c, which equals the number of coordinates minus the degrees of freedom, the number of degrees of freedom, that this equation, this amount rather of or number of independent constraint equations. Let me just repeat that. Regardless of the choice of coordinates, for a multi-body system with n degrees of freedom and n subscript v defined coordinates, if nv is greater than n degrees of freedom, then there must be n subscript c equal to n subscript v minus n degrees of freedom independent constraint equations. For kinematic analysis, we define as many driver constraints as the number of systems' degrees of freedom. Okay? This general statement of kinematic analysis can be applied to any system with one or more degrees of freedom. Now, for our case of the driven pendulum rod, let me just zoom out a little bit. The number of degrees of freedom is 1, okay? And the number of defined coordinates is 3, okay? NV is 3. So in other words, and what you see on the screen here is the column vector Q, which consists of the 3 coordinates of this mechanism, which equal the 3 coordinates of body 1, since our mechanism only contains a single body. Alright, so okay, we are busy with this equation. We have 1 degree of freedom, 3 coordinates. So what do we know? If we look at this equation, if we subtract the number of degrees of freedom from the number of coordinates, we get 2. So we need 2 independent constraint equations for our mechanism. Okay, and this corresponds to what we said earlier. Okay, this is a repeat of the previous equation that I showed in lecture 2. Okay, our 2 independent constraint equations can be written in algebraic form as shown on the screen. Okay, and we can also do the matrix multiplication, and then we get the expression as you see over here. Okay, so now it also follows that we will have to specify 1 driver constraint for the driven pendulum rod. Okay, the number of degrees of freedom, or the number of driver constraints that are needed. The number of driver constraints that is needed is exactly the same as the number of degrees of freedom. Alright. Okay, and then also what I've also indicated here is just the coordinate x1, which is the coordinate of the center of gravity, the global coordinate of the center of gravity of body 1, the x component as well as the y component. Okay, so just to recap again, we've got 1 degree of freedom, 3 coordinates, we've got 2 independent constraint equations, and we need to specify a single driver constraint for the driven pendulum. Okay. Alright. Now in general, let me repeat, in a general formulation for kinematic analysis, if boldface Q denotes an array of n subscript v coordinates, then n subscript c position constraints and n degrees of freedom driver constraints are formulated as, okay, and that's shown here in equation 12.1. Okay, now for our driven pendulum rod, the Newton-Raphson calls them position constraints. The top equation here, so boldface phi as a function of q, our position constraints have already been defined, and a single driver constraint is given by, okay, let me just, okay, and I actually already showed the position constraints just now. Okay, so this shows the positional constraints for our pendulum rod. Now the single driver constraint is given by this equation over here. Okay, and what this relates to, the orientation angle of body 1 as a function of time minus, in brackets, minus pi over 6, okay, which is the initial angle of the pendulum rod. It's minus 30 degrees. In radians, this is minus pi over 6 plus pi over 60 t squared equals 0. Okay, and this is a quadratic function that we spoke about earlier, that prescribes the angular rotation of the pendulum rod. Okay. Right, so yes, okay, and this is just written in the same form as the bottom of equation 12.1. Okay, so we've got a driver constraint equals the driver constraint functions as a function of the coordinates, okay, and in our case this is a we only have a single coordinate, one of the three coordinates of the mechanism, which is the orientation phi 1, and as I said, ft is given by this expression here in brackets. All right, now as we have already seen in chapter 7, driver constraints are simple functions of one or possibly two coordinates and the parameter time. Okay, and we've illustrated that already here as well. The first and second time derivatives of equation 12.1 yield the velocity and acceleration constraints as, okay, and that's what you see here in equation 12.2, and equation 12.3 yields the acceleration constraint equations. All right, so for our driven pendulum, equation 12.2, the velocity constraints become, okay, and that's what you see over here. So yeah, you can check the maths if you like, but I'm pretty confident that it is correct. Okay, the velocity, or the acceleration constraint equations for our pendulum or driven pendulum rod are given by this equation over here. So let's just see, it's simply the time derivative of equation 12.2. okay, yeah, okay, so this is in expanded form, given in expanded form, and you can simplify it to what you see on the screen over here. Okay, so alright, now this, and we'll refer to that, but this matrix on the left is called or referred to as the Jacobian matrix, and you will notice for the velocity constraint equations, that very same Jacobian matrix is also appears on the left, okay, as with the acceleration equations, and that is one of the characteristics of the body coordinate formulation technique that Prof. Newton-Raphson developed, okay, and it is specifically developed for not for a pencil and paper calculation. It's specifically developed for a computer implementation, for a general computer implementation. Okay, so if you write, when you write out, as we're doing here, the equations, even for a very simple mechanism, There are many terms and many equations even, but don't get intimidated by that. The fact is, having it implemented in a general purpose computer program makes the usefulness, it emphasizes, it supports the usefulness of the algorithm. We don't need to derive the equations of motion or write down the equations of motion, draw a free body diagram and all of that. We can use the general purpose algorithm as a black box. Okay. All right. So with that said, let's have a look. Yes, okay. So just this last point here, the coefficient matrix in the velocity and acceleration equation is squared, okay, or is square rather. This matrix over here, this coefficient matrix, which I've already mentioned, is the Jacobian matrix. Okay, so this, and you can see it's got 3 rows, 3 columns for the velocity, and 3 rows and 3 columns for the acceleration equation as well. Okay, so we are busy with so we're busy with the kinematic analysis, and we just showed that the driver constraints are simple functions of 1, possibly 2 coordinates, and the parameter time. Alright, and that's we also showed now for our driven pendulum is indeed the case. Now the objective of kinematic analysis is to solve these algebraic equations, the ones, this 12.1, 12.2 and 12.3, for the coordinates, velocities and accelerations for a specified time period at delta t time intervals. Okay, now Newton-Raphson in planar multibody dynamics gives this algorithm K. We sweep the parameter from t0 to t end by increments of delta t. At each time step t equals it, we perform the following steps. We solve equation 12.1 for q. Okay, if I can just zoom out a little bit. Okay, so we solve equation 12.1 for q. We solve equation 12.2 for q dot, and we solve equation 12.3 for q double dot. Okay, then we have the positions, velocities and accelerations of our mechanism. And then we compute the coordinates, velocities and accelerations of any points of interest. Okay, so because remember, these positions, velocities and accelerations are of the center of gravity or centers of gravity of each body in the mechanism. Okay. Now, on your own time, you're welcome to have a look at planar multibody dynamics example 12.1. Okay. Let's now focus on solution procedures for these equations. Alright. That is subsection 12.1.1 in planar multibody dynamics. Okay. So kinematic analysis requires solving kinematic and driver constraints at a given time t equals it for the coordinates, velocities and accelerations. The position constraints are in general non-linear algebraic equations, but the velocity and acceleration constraints are linear in velocities and accelerations respectively. Whether we solve linear or non-linear equations, we may consider 2 possible arrangements for the equations. Okay, and we'll in a minute talk about the 2 possible arrangements for solving the equations. Right, but first of all, consider the following set of two equations in three unknowns. Okay, this is just an illustrative example. For our driven pendulum rod, we have x1 and x and y1 as a function of phi1 in both cases. Okay, all right. So I'm just showing the driven pendulum rod in parallel with this illustrative example. Okay. Now assume that the value of one of the unknowns is given as z equals 3. Okay. Right. Now for our driven pendulum rod, we've got the driver function that yields the value for phi1 as a function of t. Now, equation A in our illustrative example may be considered as two kinematic constraints, which is indeed the case for our simple pendulum rod or driven pendulum rod. And equation B may be viewed as a driver expression without the presence of the time variable. Okay, in this case, for equation B, there is no time variable. But in our case, for the driven pendulum rod, there is indeed a time variable. Now, let's just look at the two arrangements that we spoke about earlier, in which we can solve these three equations. Okay, so the first arrangement, in the first arrangement, the value of z is obtained from equation B and substituted in equation A to form two equations in two unknowns. Okay, and you can follow the maths in your own time, but then we end up with equation C. Now, these equations are solved to determine the unknowns x equals 1 and y equals 2. Now, this arrangement is called coordinate partitioning method, or CP. Okay? Now, for our driven pendulum rod, at time t, we can obtain phi, the orientation of the driven pendulum, as a function of time, and then solve the following two equations. Okay, which, yeah, I've just substituted phi1 as a function of time and x1 as a function of time. Okay, or if we substitute the values of Xi A1 and Eta A1 in, Eta A1 is 0, if you remember. Xi A1 and the value is minus 0,3. We get these two equations, right? Now, yes, okay. So we can use the illustrated coordinate partitioning method to solve the kinematic, or to do the kinematic analysis for our driven pendulum rod as well. Okay, now let's just look at arrangement 2. The second arrangement. Okay, in the second arrangement, equations A and B are considered simultaneously to form three equations in three unknowns as follows. Alright, this is given or represented by equation D. Okay, now the solution to this simultaneous set of equations also yields x equals 1, y equals 2, and z equals 3. This arrangement is called the appended constraint method. Okay, now let's just quickly look at our driven pendulum example. We can formulate also the three equations, or we can simplify it further by substituting the values of Xi A1 and Eta A1, and then we end up with those three equations. Okay, now let's just look at the summary note. Although the two arrangements are not very different from the programming and computational points of view, there are advantages and disadvantages associated with each other. Okay, and you can have a look at example 12.2 in planar multibody dynamics. The point of that is the coordinate partitioning method or in the coordinate partitioning method, the number of equations and hence the number of unknowns is smaller than those for the appended constraints method. Okay, and we saw that in our illustrative example as well. Okay, therefore, the computational effort of the coordinate partitioning method is less than the appended constraint method. However, for developing a general purpose kinematic analysis program, the programming effort that the appended constraint method requires is much less than that of the coordinate partitioning method. Okay, now this is due to the fact that in the appended constraint method, the constraint equations keep their original forms. We do not need to split a set of equations into known and unknown parts and move the known part to the right hand side. Another important point is that in problems with a large number of equations and coordinates, appending one or two driver equations to the original set will not make much difference in the computational time. Therefore, in most problems, we adopt the appended constraint arrangement. Okay, and this is now what Prof. Newton-Raphson also implemented in his Matlab algorithm, and this is definitely something, or the way that we are also going with this module. Okay, now the velocity and acceleration constraints, whether we arrange them for the coordinate partition or the appended constraint method, are respectively linear in the velocities and accelerations. This is a repeat of what we said earlier. Okay, solving these equations for the velocities and accelerations requires solving simultaneous linear algebraic equations in the form AX equals C. Now, the solution to a set of simultaneous linear algebraic equations using the backslash operator in Matlab is discussed in planar multibody dynamics section 2.3.2. Okay, so it's a straightforward method, and for those of you who are interested, please refer to this section 2.3.2 in the textbook. Okay, now another useful method for solving a set of linear algebraic equations is called the LU factorization, which is discussed in Appendix A of the textbook. Okay, so this method is also useful in identifying redundant constraints or equations in case the coefficient matrix A is singular. Okay, so that's just a side note. You are welcome to have a look at Appendix A if you prefer to do that. Now, the kinematic position constraints, in contrast to the velocity and acceleration constraints, are nonlinear algebraic equations. Okay, so as will be seen in section 12.1.2, nonlinear algebraic equations can be approximated as linear algebraic equations and solved iteratively for the unknowns. Okay, so let's dive into subsection 12.1.2, nonlinear algebraic equations. One frequently occurring problem in scientific work is to find the roots of one or a set of nonlinear algebraic equations of the form given by expression 12.7. Now you will recognize this expression, and that's the reason, or the reason is that kinematic analysis of mechanical systems is one example for which the solution of position constraints in the form of equation 12.7 is indeed required. So as shown in the textbook Planar Multibody Dynamics example 5.2, the function fsolve in Matlab can easily find the roots of such nonlinear functions for us. To learn how the zeros of nonlinear algebraic equations are determined, in this section we discuss a common iterative process known as the Newton-Raphson method. We describe this process for one equation in one unknown and then for a set of n equations in n unknowns. Right, so let's look at one equation. Consider the following nonlinear equation in one unknown q. This is given by equation 12.8. The Newton-Raphson iteration for solving this single equation is stated in algorithm capital NR for Newton-Raphson 1. And you can go through the algorithm on your own. I will rather show you how it is programmed in Matlab at the hand of example 12.3. Okay, so you can clearly see that this equation is non-linear. There's a cubic term, a quadratic term, a linear term, plus a constant. Okay, and that's f as a function of x. So what does the solution look like? Okay, firstly, let's just consider the derivative of fx with respect to x, and that's given by this equation here, 3x squared minus 6x minus 10. Now, since this process, the Newton-Raphson process, is iterative, the program will ask for an estimate for the unknown x to start the iteration. So, we will enter a value, and that starts the Newton-Raphson process. For example, if we enter 10, the iteration converges to x equals 8. We may report the intermediate values of x and fx during the process in order to have a better understanding of the convergence of the algorithm. And we'll look at how this algorithm converges in a minute. An estimate of 10 for x takes 5 iterations to converge. Okay, so let's now quickly look at the Matlab code. Okay, so here you can see it asks for an input for x. It initializes the matrix zeros, and then it iterates for a maximum of 15 iterations. Okay, so we enter the nonlinear function. We enter the derivative of f as a function of x relative to x. Okay, and then we report the iteration and the convergence process. We enter the step number, the value for x, as well as the time derivative, or not time derivative, the derivative of f relative to x. And then we check if this function value, which is supposed to be 0, is less than 0,001, we then stop the iterative process if that is the case. Else we continue and we calculate the change in x and the new x value as the previous x value plus the change in x. Alright, and that's the algorithm. Okay, so let's quickly run the Newton-Raphson algorithm in that Newton-Raphson coded in Matlab. We simply enter, we just type in the M file name nr1. It asks for an estimate for x, and we will enter 10, and there it is solved. So we can quickly have a look. Results. Okay, so here you can see step 1. Let me just zoom in a little bit if I can. No. So step 1, the initial x value is 10 and the function value is 256. It iterates, or it changes x to 8.545, function value 51. Next it changes the x value to 8.0588, function value is 5.089. It then goes step 4 to 8.0008 with a function value of 0.067, and step 5, this is the converged answer for x is 8, and the function value is very small, 1.29 times 10 to the minus 5. Okay, so you can clearly see it takes 5 iterations to converge. Now figure 12.4 shows that for our function there are 3 roots. Okay, there's 8, there's something around 2, and then there's something around minus 6. Okay, so since we started with an estimate of x equals 10, equal to 10, we converge to the solution closest to the estimate. If we start with a different initial estimate, we can find the other solutions. Okay, so yeah, let's start with x equals 1. Let's see what the converged value is. Okay, if I go to my command window, I clear everything. And I say Newton-Raphson 1, initial value 1. Alright, so there are the results. Yes, so the converged value is 2, exactly 2. You can see here for our initial guess with an x value of 1, the function value is 49, and it then changes to 2, which gives a function value of exactly equal to 0. Alright, so that's that answer. Let's just see if we can find this root over here. This is approximately minus 6, so let's start with a minus 5. If I go back to Matlab or Octave, command window, I clear and I CLC and I say Newton-Raphson 1, minus 5. Okay. Yeah, so here you can see the converged value is indeed minus 6, which gives a function value of minus 3.58 times 10 to the minus 8. Alright, so that clearly illustrates what Newton-Raphson is saying here. Yes, it's actually this point I'm referring to. The Newton-Raphson method, when it works, is very efficient, but it may converge to an unwanted solution if the initial estimate is not close to the desired solution. Okay, so we saw that as well. Okay, it is also possible for the iterations to diverge. Therefore, it is essential to terminate the process after a finite number of iterations. Okay, and that's also what we saw in the Matlab algorithm. If I can go back to editor, you can clearly see here it limits the number of iterations to 15, which is a result or a precaution to diverge to an infeasible or a solution that we don't actually want. Right, so now let's look at n equations. Consider n nonlinear algebraic equations in n unknowns. This is given by equation 12.9, and we recognize the form of this equation as exactly the same form as the kinematic position constraints that we've been speaking about. The Newton-Raphson algorithm for n equations is the n-dimensional version of algorithm NR1 that you can also see on the screen and that we spoke about earlier. So, in the algorithm, we need the Jacobian matrix, which is also now should ring a bell. The Jacobian matrix is included also in the linear velocity and linear acceleration equations. Okay, and it's given by expression 12.10. So an algorithm for this process is given by Newton-Raphson in his textbook. I'm not going to go through it. You're welcome to go through it at the end of example 12.4. Just as a side note, the array inside this algorithm, they consider the array superscript I boldface phi. This array is known as the array of residuals, which corresponds to the violation in the equations of the constraint. And the term norm superscript I boldface phi smaller or equal than epsilon is the norm of residuals. Okay, and you will see if you go through the algorithm, this array and the norm of that array is used in the algorithm. Now, if the norm of residuals is smaller than the specified tolerance epsilon, then every residual is small enough to stop the iteration. Okay, so let's now look at the inverse dynamic analysis, and this is as explained in subsection 12.2 in Newton-Raphson's planar multibody dynamics. The equations of motion for a mechanical system represent the relationship between the forces that act on the system and its motion. If a specified motion of a mechanical system is sought and some of the applied forces and moments are known, it could be possible to determine the remaining forces and moments that cause that particular motion. When the desired motion is known and the objective is to find the unknown forces and torques, the process is referred to as inverse dynamic analysis. Inverse dynamics is an extension of kinematic analysis in which the reaction forces and the unknown forces and torques associated with the driver constraints are determined. The fundamental process for inverse dynamic analysis is the same, regardless of the method used to formulate the problem. Inverse dynamic analysis of a multi-body system requires a kinematic analysis to be performed first to determine the coordinates, boldface q, velocities q dot, and accelerations q double dot. And these are obviously algebraic vectors, which is the reason for them being printed as boldface. Now, if q, the algebraic vector q, column vector if you like, does not contain the complete kinematics of all the bodies in a system, in the case of a vectorial formulation, for example, the body coordinate arrays of, and now Newton-Raphson chooses to use C, C dot, and C double dot, must be determined prior to performing the force analysis. Alright. The equations of motion for a system based on either the body coordinates from equation 755 or the free body diagram method can be formed as, and there you can see the equations of motions. It's the mass or inertia matrix multiplied by the accelerations, the centroidal accelerations of the mechanism, of all the bodies in the mechanism, equals the applied forces and moments plus the transpose of the Jacobian matrix multiplied by the Lagrange multipliers plus the Jacobian, the transpose of the Jacobian of the driver constraints multiplied by the driver Lagrange multipliers. Now, the Jacobian matrix and Lagrange multipliers associated with the driver constraints are included but separated from those of the kinematic joints. For our driven pendulum rod, it follows that, and there you can see, this is now the equations of motions written out as algebraic in an algebraic matrix form. So you see the mass or inertia matrix multiplied by the centroidal accelerations equals the applied external forces and moments, and here it's only mass times gravitational acceleration, and it's in the negative y direction. Okay, what we have here is the Jacobian matrix of the kinematic constraint equations, the position constraint equations, the transpose of that Jacobian, yes, multiplied by the two Lagrange multipliers, plus the transpose of the Jacobian of the driver constraints, single driver constraint, multiplied by the single Lagrange multiplier, driver Lagrange multiplier. Okay. Now, these equations of motion, referring back to the algebraic equation that you see here at the top, can be rearranged in this form. Okay, where we have the two Jacobian or the two transposed Jacobian matrices, the kinematic constraint equation Jacobian matrix and the driver Jacobian matrix transpose of both of them, Lagrange multipliers of the constraint equations, Lagrange multipliers of the driver constraints, and on the right hand side of the equation mark we've got the mass or inertia matrix multiplied by the centroidal accelerations minus the applied forces and moments. Okay, so for the driven pendulum rod, equation 1211 can be written as so what you see here, this is a square matrix consisting of the transpose of the two Jacobian matrices. We've got a column vector consisting of the three Lagrange multipliers, and on the right hand side of the equation mark we've got the mass or inertia matrix multiplied by the centroidal accelerations minus the applied external forces. Now, since the coordinates, velocities and accelerations are known, the coefficient matrix and all the terms on the right hand side are numerically or can numerically be evaluated. Okay, so the only unknowns that we have are the Lagrange multipliers, and that's the next line of thought that is listed here. The equations are solved as a set of linear algebraic equations for the Lagrange multipliers. Now the results for the transpose of the Lagrange multiplier, the transpose of the Jacobian matrix multiplied by the Lagrange multipliers provide the joint reaction forces and torques, and the transpose of the driver Jacobian matrix multiplied by the driver Lagrange multipliers yields the forces or torques associated with the driver motor or motors. Now, let's have a look at our driven pendulum example once again. The joint reaction forces and torques, joint reaction, and remember there is only a single joint, that's the revolute or rotation or pin or hinge joint, so that the joint reaction forces and torques are then given by the transpose of the Jacobian matrix multiplied by the two Lagrange multipliers. Okay, and here I've yes, this is the I've multiplied it out. This is the expanded form then of the resulting column array or column vector. And what I've done here, yes, I've just substituted the values of CA1 as minus 0,3. Okay, and what I also did here, I eliminated the eta A1 terms because they are for our driven pendulum rod 0, or Kasi eta, eta A1 is 0 for our driven pendulum. So these two terms fall away. It's only the Kasi A1 terms that remain. Okay, so let's just have a look. Yeah, this just shows you what I just said in words. So for this driven pendulum, there's the eta axis indicated here in a dashed blue line. This is the Kasi axis, also in a dashed blue line. So the eta coordinate of point A in body 1 is 0. As you can see, it's in line with the Kasi axis. And the Kasi A1 coordinate is minus 0,3. That's where that comes from. Right. Now, to continue then, for the driven pendulum rod, the torque associated with the driver motor is given by simply by 0,01. This is the transpose of the driver Jacobian matrix multiplied by the single Lagrange multiplier lambda 3. So the torque associated with that driven motor is exactly equal to lambda 3. Okay, and what you also see, right, so what you can also then see, maybe let's just first finish talking about this quickly. So if I can go back to our simulation that we run. Okay, if I can just go back here. Yeah, so let's first consider the input torque. So the input torque required to result in the prescribed motion for this pendulum rod is exactly equal to lambda 3. That's what we just saw. Okay, if I can go back quickly, that's what we see. The torque associated with the driver motor is given by lambda 3. So I've just added this column, and all I did was I set this cell value equal to the lambda 3 cell value for all the time instants. Okay, so that's very easy. Let's just look at the reaction forces in a bit more detail. So if we look at the reaction forces and moments associated with this revolute joint, the question is, why is there a moment or a couple? Why is there this term over here? It's easy to understand, and now we can see the reaction force in the x direction is indeed minus lambda 1, and the reaction force in the y direction is minus lambda 2. Okay, so but why is there a moment or a couple? Okay, the reason is we've in effect replaced these two reaction forces in the x and y direction with parallel and equal reaction forces at the C of G plus a moment. Okay, and we can do that, or to understand that, let's just consider another book written by Professor Newton-Raphson, Computer Aided Analysis of Mechanical Systems. This book was written in the early 80s, and he explains it in chapter 8. Okay, in this figure 8.7 over here. So replacing the given force in figure 8.7a, so there's the force F acting at point A. We replace that force by an equal parallel force and a couple to compensate for the change in the moment of the force. Okay, so there was the original force. We replaced it with an equal parallel force at position B. Okay, and then the couple is a result of this minus of that force and the original force. That's the couple. Okay, and then the net effect is exactly the same. The net effect between figure 8.7a and 8.7c is exactly the same. And this is what happened over here. Okay, so that's where the original force in component forms acted on body 1. We replaced them with equal and parallel forces at the C of G plus a couple. Okay, and if you look at this term here, okay, it's the couple is minus 0,3 times lambda 1, which we know is minus 1, or is, sorry, is that's the force. That's the force, but in the negative direction. Okay, times sine of phi 1. Okay, let's just have a look. Minus, okay, sine phi 1 is minus, so it's a minus times a minus times a minus, so that gives a minus. Okay, and that is exactly the same. I mean, Fx is acting in this direction, so the moment about the center of gravity associated with this force Fx is in the negative direction. Alright, and similarly, let's just have a look here. Lambda 2 is in the negative, or is the negative of Fy. Okay, so that's a minus. Cosine of a minus is plus, so this is then also a negative moment. Okay, the moment associated with Fy about the center of gravity is in the clockwise direction, and hence it is a negative. Okay, so that's just a brief explanation of where this term comes from, but we are really only interested in lambda 1 and lambda 2 and how they relate to or the reaction force minus lambda 1 and minus lambda 2, because that's in the x direction, this is in the y direction. We are not interested in this moment. Okay, so if we go back to our spreadsheet, so the reaction force in the x is then simply minus lambda 1, okay, and the reaction force in the y is minus lambda 2. Okay, and that's what I've done here. So, and now this corresponds exactly to our analytical calculation, which is reassuring. Okay, and we can then obviously also calculate the resultant reaction force by taking the square root of the sum of squares of the two components. And done here is I've plotted the reaction forces and input torque on a single graph. The reaction force in the x direction, Fx, is plotted in blue against the primary y-axis, and the reaction force Fy is plotted in red also against the primary y-axis. I've then also plotted the resultant reaction force in purple, and this overlays, or the reaction force Fy is actually overlaying the resultant reaction force. Okay, and that's why you don't distinguish clearly between the red and purple lines. But be that as it may, what is also plotted on this graph is the input torque in green, and this is against the secondary y-axis in Newton meters, and it also oscillates, but the amplitude of oscillation remains constant, approximately 12 Newton meters from +6 to -6, although the period of oscillations shortens as time goes by. And this response is exactly in line with what we saw with the plot of the coordinates of driven pendulum rod, as well as the velocities, as well as the accelerations. Now, if we look at just this graph quickly, so we specified, as you know, a constant angular acceleration as an input for this driver function. And looking back at this hand-drawn schematic that you see on the screen at the moment, it makes sense intuitively also. It makes sense. If we do a sanity check, we've calculated this input torque as an oscillating input torque, and that makes sense because it is associated, or this mechanism is a single body rotating around a pivot point, and we can clearly understand and understand the physics that as you pull the pendulum rod up, as you lift it, you will need more torque, and as the pendulum rod is falling on the other side, you actually need to reverse the torque and make and reduce the acceleration. Make sure that the pendulum rod does not accelerate as further. Well, it cannot accelerate, or it cannot accommodate a change in acceleration as it goes around. So the behavior that we see and the calculated values of the input torque intuitively or as a sanity check does make sense. Obviously the maths and the algebra is correct, but we also always need to do a sanity check to see are the results that we obtained correct. Okay, so in our next lecture what we will be doing is we will be applying a torque to the pendulum rod and then calculate the response, right? And that is referred to as forward dynamic analysis. Okay, we now focused in this lecture on doing and performing the inverse dynamic analysis, where we specified a specific motion and calculated the torque required to generate that motion. For the forward dynamic analysis, we're going to specify a torque and calculate the response for the mechanism. So until then, thank you very much for watching.